Here's a solution to homework number 9, problem 1 in ME370. And I have this breakaway door handle made out of ASTM number 20 gray cast iron. And it's got the loads and dimensions that you see here. You know, it's got 15 pounds of axial and 35 pounds in the Y direction. It's got this little portion right here, this little machined portion, and it's meant to break there, right? So it's purposely breaks so that maybe it protects the door or whatever from getting damaged. So the distance in the little gap right here is A is 0.3125. This distance B is 2.5 inches, and this distance here is 6 inches. And the small diameter 0.75, the large diameter 1 inch, and then the radius here, the little fillet, very, very small, 0.0125. And we want to find the safety factor in two different spots, right? Well, where it's the highest tension and the highest compression. Yeah, I think did I express that the right way? Plot these 2 points: largest tension and largest compression stress element. Okay, yep. And you may need to adjust the scale extents to make it remain a symmetric graph. All right, so there you go. One of the first things I will do, I'll turn my camera on. That'd be good. Okay, come on, camera, you can do it. Just thinking. Just gonna open it up. There you go. All right, so here I've repeated the problem in a little bit of detail. Put my name and everything up there, make it nice and neat. So one of the first things I might do is find the material properties. So we get out our good friend Shigley here and look up in the back and find gray cast iron. And I think it's A24. That's my recollection. Right here inside. And we have number 20, right? I say number 25 or number 20? I think it's number 20. Number 20. So we have 22 KSI in tensile strength, 83 in compressive strength. So I'll write that down. So maybe I'll write it up here. And tensile is my short attention span, 22 KSI. I totally forgot what it was. And we had 83 KSI. Okay. We also know that there's a stress concentration here, so we might as well look up while we have the book out. Might as well look up what that stress concentration is going to be, or at least see what the parameters are that we need. We see that we have this one right here. Looks a lot like our situation. I even labeled them the same. That wasn't very nice of me. And we're going to use R divided by T and A divided by T. And if you look really closely, you'll see that's the T right in there. So it's sort of like a thickness, if you will. So if you take big D minus little d, and then you divide that by 2, you should be able to get that thickness right there. We also notice that we're going to use this as the nominal stress that we're going to take this multiplier, the stress concentration, and multiply it by. So our first maybe priority is to get with that AT and that RT. And we might notice that this is for combined axial and moment being placed on there. And then we also see that we have torsion over here, and it too is using the RT and the AT. And here's your nominal torsional shear stress. So let's find that AT and the RT first. So first you need T. So T is going to be, like I said, big D minus little d over 2. So we're going to have 1 minus 0.75 divided by 2. And I'm kind of squeezing this in a little tighter than it needs to be. I can use lots of paper, so I don't need to be that. But I went ahead and did it. I think T is 1/8 of an inch. Okay, so our A over T. A, we were told, is 0.3125. divided by 0.125. And I believe I'm going to get 2.5 here. Let's see. Yes, I do. I believe. Little trust issues in my own. Yes, 2.5. Which I did on purpose. And then R over T. We're going to get, see, R is 0.0125 divided by 0.125. And you get 0.1. Once again, I did that on purpose. All right, so I'll write this down from figure A15 16. And we will try to find that as best we can. All right, so we might want to zoom in here a little bit. Let's see. There you go. Boom. My method of zooming. And we see here's 2.5 right here. And coming up, and we have 0.1. R over T is 0.1. And we have 2.5. And we could see that we get something close to, I decided that it was 5.1. Right, so here's 5.5. So what you could do in lightly is you could kind of like count through. There you go, like 1, 2, 3, 4, maybe something along those lines. It might be a little bit bigger than 5.1. I used 5.1, so I'm going to stick with those numbers. But 5.15, 5.2, maybe you could argue that really closely. If you really wanted to get very, very detailed in it, you could use a micrometer or a caliper, I should say, digital caliper, and actually measure it, and then like measure the distance between here and there, let's say, and then figure out what the fraction of that would be, and then you'd be very, very exact, or very more closely exact. But you get 3 people to do it, and they'd all measure different things. So there. I'm going to say 5.1. And then this next one is figure 1516. And we can make a designation that's a little differently, because you'll note that there's an S there for shear. Right? And in this one, let's see, 2.5 and 0.1 is almost exactly 3. It's like I planned it or something. Because I did. Ooh, this stomach's making noise. There you go. Okay, so there's 3. And now I need to get some the stresses, but now I need the loads next. So I would almost consider all of this, and I might label this, if I hadn't scrunched it up here, the geometry aspect of this thing. I could also get the area and the moment of inertias and stuff, but you'll see that we don't need them, because the equation we're going to use from the caption, the stress, the nominal stress in the caption doesn't has it already kind of built in that for the geometry. So, but we go to the loads portion of this, and I want you to do the right thing here, so maybe I should model that, and so I will. And that is to make a free body diagram. Don't skip out. So one thing we would note. Let's see. Let's just take a look. First, maybe I want to do the XY first. So I'm going to do an FBD in the XY. And I'm often looking for, and I'll make a detailed one. I'm often looking for problems that I can maybe not trick you, but kind of get you into, give you the experience of making the mistake of not doing a free body diagram and seeing what the consequences are. But that would inevitably be kind of a complicated problem, and I don't want to give you terribly complicated problems. But I do want you to see that it's a pitfall to fall into, to not do the free body diagram and discover that you get the wrong answer because you overlooked something. So is this being methodical that's really going to help us. All right, so I'm going to replace this with the correct values, and that's going to be 35 downwards and 15 this way. But I know that, like, you could totally some of these problems, it's kind of just obvious, right? This reaction moment, it's obvious, right? It's just going to be I'll call this the moment about the z-axis, and I'll even call it RZ. All right, so summation of moments about z is going to be the reaction moment, right? That's the thing we want to find, minus 35, and that distance is b right here. I guess I'll kind of try to put it in there. And that distance should be 2.5 inches right in there. And not a thrilling result, but worth calculating. Am I that lazy? Am I just going to do it this way? Yeah, sure. I think it's 88. Should be 88. I have mine on here. I have it in Excel. That's what I'm looking at over here on the side. Oh, 87.5. Look at that. 87.5 inch-pounds. And let's see. Let's take a look at let's look downwards at this thing. So let's look in the XZ plane next. And I'm not going to be able to scrunch everything in here, am I? That's okay. I have more paper. Alright, so we're looking down at the piece. And I'm even drawing this little thing in there so you can kind of see that's where we're going to expect the stress to be the worst. And this is the XZ. And we can only see this force right here, right? That force in the X direction, which is the 15 pounds. And we'll only be able to see the RX. And I know what, I'm not even going to bother solving for the RX and the RYs. I knew what those were. It's the moments that I really care about. And so that one is going counterclockwise. So this one better go clockwise, right? I got that right? Yeah. So this is going to be MRY, right? Reaction moment about the Y. And the distance that we need right here, this is going to be the 6 inches. All right, 6. So the sum of the moments about the y-axis, and we have the reaction moment, which is negative, and then plus our 15 times 6, and I should be able to do that in my head, but I don't trust my head. And I say it's 90. Did I do that correctly? I think so. Yeah. 15 times 6 is 90. Sounds right. Yeah, I need inch pounds. All right, let's go to the next page. Something we would know right away, though, is there's 2 different bending moments, so we have to take the magnitude of those bending moments. So it's going to be the square root of this squared plus that squared. So we're going to page 2 here, and we do another free body. Here's problem 1 continued. ... And let's see, we're going to look at an FBD that's going to be looking down the x-axis. So we'll be going YZ over to the side. Right? YZ. So we're looking in that direction, and we're going to end up finding the torque in this one. Not an exciting free body diagram. And is it 100%? Whoops, boy. It's a straight line. Is it 100% necessary? I think it is. All right, so there's the thing that we're looking at, and here is our Fy, which is going to be 35 pounds. And this distance right here, okay, that distance is 6 inches. Right in there. I didn't make this one as pretty as the others. There's a stomach again. I can always up with that. Didn't like breakfast or something. I don't know. R Y, and then we have this moment. And which way is it? That's going counterclockwise. So this one must go clockwise. I'll make the head over there. So here's him. R X, which is the same thing as the torque, right? So the summation of moments about the x-axis. And we have a negative MRX and a positive 35 times 6 equals 0. So our MRX is, let's see, where'd you go? 210? Let me double check that didn't have another decimal place. It shouldn't. It should just be 210, but 210 inch-pounds. Okay, so now I'm ready for the stresses now that I got all the loads. Well, one more thing. I'm going to have the maximum moment. Maybe I'll also say that this is equal to torque. The maximum moment is going to be the square root of my 87.50 squared plus my 90. Right? 90 squared. And I already have that written down there somewhere. I say 126, got another decimal plate for me, 125.5 to get 4 sig figs, inch-pounds. Now we can go to stresses. All right, so we did loads, we did geometry, loads, and stress. And now we're going to use the equations, and I can do this in one step right here. So I can, and I know, but I have to be careful because I said I want to be in tension and compression. The axial force on this is that Fx, right? And so it's always going to be tension, but the bending can sometimes be compression. So we need to do this thing with those equations. Need to do it twice. So for write this out. Max tension is going to be this one, and I guess I'll write it as max. Is going to be KT times, let me look at the equation again because my short attention span. 4F divided by pi d squared. I could just have remembered that. And we're going to add in 32m divided by pi, it should be d cubed. I get that right? Yeah. So, that's going to be our 5.1 times 4, and that F is only 15 pounds, so it's not going to be a lot. Pi, and we're going to use the small diameter 0.75 squared, and then take our 32, and the moment's going to be our 125.5. and divide it by pi and 0.75 cubed. So we should end up with, let's see, I didn't bother doing it this way. Did I? I think I get, let me see, boom. Yeah, it should be 15.63 KSI tension. All right, and then I'll go max compression. And I didn't bother with my writing all the letters out there. Look at that. max C, and it's all the same thing. I shouldn't even bother with this, but I'm gonna minus. Apparently, I didn't make my mind up until I just started doing it. Alright, and 5.1 415 pi 0.75 squared minus 32 125.5. Is this necessary? I don't know. I could have done this so much more briefly, but it didn't. So I only get we get a very slight difference, and I'm not going to even put the negative in there. I'm just going to put down here. All right, so there's not much difference in terms of the overall magnitude of this. And then we just go torsion. So go tau. I'll say max, but remember that's not really the abs max. I'm just saying it's KTS, and that equation should be 16 T over pi d cubed. So here we go, 3.0 is what we got for that stress concentration. The torque we just found to be 210. And what else? Pi 0.75 cubed. And we can actually just put this over to the side, have enough room. And that's going to be 25.78 KSI. All right. So we should do the principal stresses for these, the two principal stresses. So so maybe I'll write that out. Principal, because it's like your pal, just like the guy in charge of the school, or lady in charge of the school. I guess it's plural, principal stresses. So I'm going to do this in miniature. Save a little space. So here is the tension one, which is along the x-axis, but we don't know actually which direction that's going to be. And I think the stress element will always be like that right there because of the orientation of that orientation of the torsion. So this is our 15.63 KSI and the 25.78 KSI. So in my miniature Moore circle, which I'm really just using as a mnemonic to try, kind of a mnemonic, I guess you'd say. It's going to look something like this. It's just a way to like remember. I guess it's mnemonic then, isn't it? That's what mnemonic is. And here's Mr. Laziness. I'm going to just put a little circle in it. It's closer to that one, probably. I guess I think it's going to be closer to this one. Yeah. It hardly matters, right? It matters to somebody somewhere. Sigma A is right there. Sigma B is right there. And here's C, and that's going to be R. So we say that we have C is going to be equal to 15.63 divided by 2. Did I do this? I don't know. No, I didn't bother. I did it with just a straight equation. So I'll go ahead and do it. Why not? 15.63 2 divided, and we get 7.815 R is going to be this right here. So it's going to be this leg, which is C, and that leg, which is tau. So square root of 7.815 squared plus 25.78 squared. And 25.78 squared atom square root. You get 26.94 KSI. So sigma A is C plus R. Sigma B is C minus R. Okay. And for this, it should come out to 32.96 KSI in tension. And this is going to be a, you know, I'm going to leave it as positive and negative because that's how we're going to use it here in a minute, I guess. That makes sense. We get a negative 20.17. Is that correct? I think so. I'm just looking at my. It just seems to me. I just want to point out. I just want to double check something on here. Oh, I can't. You can't even grab it. Where'd it go? Where'd it go? This guy. Ooh. I made a mistake here. Oh, my bad. That is not correct. That is a previous problem I'm looking at. That was silly. I should have done by hand, right? Oh well. But I think I got the right thing, right? So add these two together, 26 and 7.815, and you should get. Oh my! What's going on here? What did I do wrong? Oh, I need to go backwards. I think I wrote down all these numbers incorrectly. No, I wrote those correctly. That's correct. This one's wrong. This one is wrong. Oh, how much did I do wrong here? I should have. Oh, this guy. Accidentally erased that. All right. Well, I don't have this video just gets recorded from Ensemble, so I don't really want to go through the video editor and change the thing out. Let me double check what this one is right here. 210 16 times 3 times pi divided 0.75. Oh, nuts. Let me get rid of that. I need to enter 3, raise it to there, and then divide. I get 7. Yes, that's the correct 7 point. Let me see. Let me escape out of that and go to this. Give another decimal place. Yeah, 7. So sorry about that. 7.605, and so this should be over here. Should be 7.605 KSI. Yeah, and then I said like 15.63 KSI. Okay, so that was correct right here, but this was wrong. 7.605, and so let's make that squared and our 7.815 squared atom square root. I should get a different number than I just got. Son of a. Say that again. All right, so do this one more time. 7.815 squared and 7.605. Oh, I know what I just did wrong. Squared plus, yeah. 10.90. So that plus 7.815 should get me, yes, the 18.72. 18.72, and then if I subtract them, I should get a negative 3.090 KSI. I could show you why I got this wrong as I make them in Excel, and I had two different problems. I had one over here on the left and one over here on the right, and so I looked at the one on the left when I should have been, maybe I should just hide it, and I wouldn't have looked at the thing. So let's take a look at the principal stresses in the other stress element. And I think I'm doing this if I can give you a justification, just so that you kind of reinforce or have in mind that we have, we're on the lookout for this worst stress element, and that we could possibly have had, it's not likely, if we had compression, a large amount of compression on an axial direction compared to the bending, we could come up with a scenario maybe where this stress element would be the one that would fail, whereas the other one wouldn't. It probably would be kind of obvious, but maybe not. All right, so this one's going to be 15.28 KSI, and this will be still 7.605 KSI. So doing a very similar, yet a little slightly different thing here. All right, so maybe I'm going to cheat, and let's see, I'll use the same size. There you go. I'm going to cheat. Shh, don't tell anyone. There you go. And now I know that I'm going to be something. Try to make it look near the center. I didn't pick out where the center was, but it's like that. There you go. There's the C. I'll use that as the R. Sigma A. Sigma B. Right there. So let's say that C is just going to be a negative 15.28 divided by 2. And that's a negative 7.640 KSI, but I don't usually use them. Anyway. So the radius here is going to be that distance right there, 7.640 squared plus my 7.605 squared, and so we end up with 10.78 KSI. So my sigma A is equal to C plus R equal, and we add those two together, and we should get 3.1 something, 3.140. 3.140 KSI, and sigma B can be C minus R, and we would get a negative 18.42. Not much different. They're pretty much flip-flopped from on either side of the thing. But I could have somehow gotten creative and made them so they were significantly different. And might as well finish up on a fresh sheet of paper here. We're only looking for brittle Coulomb more, right? I didn't ask you for modified more. So for the compression side, tension side, and this is one continued, whoops, dot, tension, or max tension. So the max tension, the equation for brittle Coulomb Moore safety factor is sigma A divided by the ultimate in tension minus sigma B divided by the ultimate in compression. And you can even just memorize that, right? Because the apples and apples idea, right? And the negative is there just simply because this will be negative, so whatever. So you just take brittle Coulomb Moore here, and sigma A is 18.72, and we're going to divide it by the ultimate 22. So it's pretty close. Then minus, and now we go minus, because it's the minus 3.09 divided by 83, right? So it's not going to have a large effect. But I tried to make it so that it would fail, I think, or get close. Get close to failing? Is that what I tried to do? Yeah. So I say that it's 1.13. And I'm not going to put any more than 2 decimal places there, right? And then the max compression. Lazy. 1 over n. All right, so the equation isn't any different, but the values are here. So we're going to use 3.140 and divide still by 22, and then minus, and there's a minus 18.42, and divide it by our 83. And we get a brittle Coulomb Moore safety factor of 2.74. So I'll rewrite out my answers because I prefer when you do that. So max tension, brittle Coulomb Moore, is 1.13. Max compression, brittle Coulomb Moore, 2.74. And I believe I said that I wanted you to do the to show me the I'm trying to think of the words the failure loci. All right, so let's see, and I said from homework 8 we had this spreadsheet right here. If it'll open up, there you go. And let's see, we have 22 and 83. And it looks like it's symmetric, right? Albeit it's not all that pretty. So I'm going to go print this out. I'll pause the video. See. Oh, wow. Why are you doing that thing? Okay, he didn't like that. I'm going to print him out. And you'll see that it defaulted to printing it out correctly, right? I think it's still symmetric. Okay. So I'm going to print this out. I'll pause the video and come right back. You don't need to see my code. Okay, let's see here. So we're going to plot these points out. The first one is, let's see, from here, we can see we have 18.72. So right here we have, what are we counting by? 1, 2, 3, 4, 5. So we're counting by 4s, right? So right here is 16, and we're like 18.72. So we're really, so right here's 16, here's 18, like halfway in between there, and we are very close to like right in there, right? And then we have 3, which is, okay, we're counting by 4s. So, you know, here's 2, and here's like 3 right there. So right about there is the point. And I think I just decided that I was just going to go with it instead of trying to make it like a really like impressive like result right there. It's just we've already. I think maybe you've made the impression has come upon you from a homework 8, where that you could see the failure loci and the usefulness of it. But this is just a visualization of what these boundaries look like. Another way to try to cement the idea of a safety factor. Okay, so now we want to go this one. Now that's the same dealio. Here is going to be 18, and this is actually closer to the 18, so maybe make it like right in there. Okay, that's 16, that's 18, so like right, it's closer to 18 than it is to 19. And then the other one is 3, which is once again like right here. So we're going to have a point somewhere like right in there, right? So you could see how far away this one is to right there. And I don't think I asked you to graphically confirm it. Let's see. Plot these 2 points on a brittle stress envelope and graphically confirm. I did say that. What a pain in the ass I am. Okay, so this is going to be 0, and I might call this A, and I might call that point B. And I just wrote C. I said B, and I wrote C. And then I'm going to call this one A, and I'm going to call this one B. I could call them different things if I wanted to. And I could say that the brittle Coulomb-Moore tension, right, is approximately, all right, so first off, I'll write this OA is approximately, and I will measure this thing out here. As near as I can tell, that looks like 2.1. I'm going to call it 2.1. And then for B, I'm going to call that, geez, let's see if that's 1, 2, it's almost 2.3. So that would be 2.3 over 2.1. What do I get? It's probably not going to be very great. I mean, 1.095, right? So 1.10. So there you go. That's we had 1.13. So we can. I'm buying it. Okay, cool. Graphically, see, confirmed. And then this other one, we could go for OA. Like I could have named it something else too, I guess. That should actually be the same radius. That should actually be 2.1, by the way, if I did it correctly. Oh, no, it should be slightly different, right? Because they are just ever so slightly different. Okay, so maybe, yeah, maybe not. So that looks like a 1.9 to me. And then B, we get 5.3. Oh, it looks like 1, 2. I'm looking up on the screen here. I'm gonna go 5.3. So B compression, approximately. There you go, approximately 5.3 divided by 1.9. And 5.3 and 1.9, boom. How far off we get? Oh, not too bad. 2.79, call it. You can see I got 2.789. It's 2.79. And so that's confirmed. Put a little R in there. All right, so I'm going to make another video for the next problem because this one went way too long. That one's probably even longer. Oh well.